Hello students, today we will start unit unit 2 of computer organization. In unit 2 we have subjects like addition and subtraction of using ones and twos complement methods, binary adder, one topic, another topic is parallel adder, the next carry to ahead adder, multiplication using Boo's algorithm, division, floating point operations. So in this session we'll start from binary adder. So let's discuss about the binary adder. So binary adder is a circuit which is add two or more binary numbers. Okay, it is of two types. One is half adder and full adder. In case of half adder, there is 2 bit is used for addition process, and in case of full adder, there is 3 bit of binary numbers are used for the addition process. So let me describe what is the meaning of this 2 bit and 3 bit. Okay, suppose I have a number 0 and 1, and I have to add with another 2 bit number, that is 1 and 0. When we add these two numbers, this 1 0 will be 1 and 0 1 will be 1. So this is our result, it is the addition result, but these two are our input value. Okay, so if we see in column direction of this addition process, then it is a 2 bit number. This is the first bit, this is the second bit. So instead of this procedure, here I can explain it as 1 and 0. So this addition is okay, this is my first input, this is my second input. When I supply this two input number, I will get the result. Okay, but as in case of 3-bit number, okay, suppose the addition is like that: 0 1 and 1, or say it is a 0. So if I add this 3-bit number, so say this first bit is called A, the second bit is called B, this is called C. When I add this ABC, I will get the final result as 1. This is my result. Okay, so result is in S. So for this case also, we have two input values as A and another input value is B. Okay, so we will get the result S as its result, that is a sum. So in half adder we can do this addition process. Okay, in case of half adder, and in full adder we can do this addition process. The only difference is that in case of half adder we have 2 bit. Okay, in case of full adder we have 3 bit to input it. Okay, okay, this binary adder is a combinational circuit. Okay, we'll see it. So in case of half adder is a combinational circuit which adds 2 bits of number. So in last slide I said one number is A, another number is B. So this is the block diagram of half adder, and it is a combinational circuit. It means that the output not depends the output only depends on the input. Okay, the current input value. Okay, so this is my first A is my first input, and this is my B is the second input terminal. Okay, I can supply only 2 bit to the system. Say for example A is 1 and B is 0, so that this system will receive 1 0, and it will add these two number. Okay, then it will produce one value is sum, another value is carry. Okay, and when we add these two number, in some cases we'll get the carry of the carry value. Okay, so as this system have two input values, then the possible combinations are 4 as per the rule 2 to the n rule. Okay, here n is the number of input value. So we have 4 possible combinations of input, or 4 possible sequence of combination of input value to the half adder. So this is the functional diagram. So in this functional diagram we have the 2 input values. These 2 are input value, A and B. Okay, and this is our output value. S is output value and C is output value. So here S is just it's called sum, SUM. Okay, and C stands for carry of the sum. So for first sequence the input value may be 0 0. For second sequence it is 0 1, and third sequence it is 1 0 and 1 1. And apart from that we cannot add more number of sequences. Okay, so that is 2 to the n. So when we add these two number a plus b, that means 0 plus 0, we'll get 0 and carry 0. Suppose I have a number 0 and another 0. Okay, this is my first a number, this is my first second b number. When I add these two numbers, I will get 0 as sum and 0 as carry. Okay, so see what is the meaning of carry actually. Suppose I want to add 15. If I want to add 15 plus 7, these two decimal number, I have to add these two decimal number, then I will get that 5 plus 7 equals to 12. So instead of writing 12, I will write here 2, and okay, this is my result 12. I will write this 2 here, and this one is a carry, and this one will move to the next column, next addition column. Then 1 and 1, it becomes 2. Okay, so this is called carry value. Similarly, when we add these two binary number a and b, we are getting s as sum and 0 as carry. So this is a sum value, this is 0. Again we can have a equals to 0 and b equals to 1. In that case we will get the sum is 1 and carry is 0. Okay, and we may have a equals to 1 and b equals to 0. The sum is 1 and carry is 0. Okay, so when a equals to 1 and b equals to 1, we are getting sum equals to 0 and carry is 1. Okay, so see, when I add these two number 1 and 1, this value is 0 and 1, becomes 1 0. So this first number is sum and the second number is carry. Okay, so this is our functional table. We just evaluate, we got this functional table by just putting the input values to the half adder. Then we evaluate that what is the sum according to the value of a and b, what is the value of c according to the value of a and b. Okay, so after that we have to find that, or we just look at the s column, that is sum column, at which case the sum column is an active state. Okay, so in both time the sum is an active one for this one and for this one, and we have to look at that for this one what are the values of a and b, and for this one also what are the value of a and b. Okay, so just check this first one. Okay, for this first one a is 0 and b is 1. So as you know that 0 is represent the complement form and 1 is represent the non-complement form, right? So here we have to write a not b. Okay, we got the first sequence. Then we have another one in the s column. Okay, for this sequence or for this combination, we got that a is 1 and b equals to 0. So b is a not form, that is a b not. So thus s equation will be s equals to a not b plus a b not. Okay, similarly when we look at the column side or carry column, okay, at one place only the carry is active. When the carry is active, that time both A and B holds one value here. Okay, so that C equals to AB. So this is my second equation. So this equation is for half adder. From this equation we can draw the circuit diagram. So before doing the circuit diagram we have to think about the block diagram. Okay, from that block diagram we got the idea about the input values and output values, and from that input values, when we supply the input values, so we can evaluate the functional table, and from the functional table we have to find the out the boolean function or logic or boolean equation, or you can say it is a boolean expression, and from that expression we have to do the circuit. Okay, so first we have to do the s. For finding the s value we have two input values A and B. Okay, but these two input values are in different form. Some are non-complement form and some are complement form. Okay, so here in first case this A is a complement form and B is a not complement form. So first I have to draw a NOT gate just to find out that the NOT form of A. So this is my A value, and when I supply this A value through this NOT gate, I will get A NOT or A complement. So I can write here this way also. Okay, instead of just like this, I can write this. So another input value for this combination is B. So here B, and both are perform an AND operation. Okay, these two perform the AND operation. So this AND operation. Okay, this is my B. It will perform the AND operation. After that, we're thinking about the next pair of sequence, that is A and B naught. Here my A value, I can supply this A value directly, and this is the B naught value. I have to do, or I have to connect NOT gate with the B, and both are AND operation. Both will do the AND operation. Okay, after that I will get A naught B. At this case I will get A naught B. At this case I will get A B naught, and after that we have to do the OR operation. This is the OR gate. We got S. So here S equals to, this is the equation, A naught B plus AB naught. That means we can supply this value to this circuit, 1 0 0 0 0 1 and 1 1. So according to that we will get S value. Okay, so similarly we can do the circuit diagram for this equation, that is C equals to AB. It's very simple. There is no not form are there. Okay, it is the AND operation, that is A, this A, and this one is B. Okay, and this. So just look at this. When when I give A equals to 0 and B equals to 0, what is the value of C here? The C must be 0, because in AND operation A is 0, B is 0, the output is 0. Okay, this one, the output is 0. When I say A is 0 and B is 1, instead of this 0 I can write 1 here. A1, still I am getting 0, because in AND operation or AND gate, if I supply any one terminal is 0, then output is 0. Okay, for this sequence here A is 1 and B is 0. Still I'm getting 0. This one. Okay, but for the last pair of sequence, input sequence, A equals to 1 and this B is 1, then I will get the value as C equals to 1. Okay, so I prove that this circuit diagram perfectly works with the output when I supply the input value according to that input sequence. Okay, okay, we can prove this circuit diagram also by just providing these two input values. Okay, say just look at this one. When I supply A equals to 0, A is 0 and B is 1. Okay, B is 1. In through this NOT gate, when 0 is supplied here, that becomes 1. Okay, in this one, so it will produce for this not AND operation, the input value is 1 and this one, and it will produce the result 1 here. Okay, so this B is 1 and this B is becomes 0 because this NOT is connected here. Okay, because B value is 1, through this NOT gate it becomes 0, but here A is 0, A is 0, and this A is directly connected to this gate, that is 0, and this AND gate receives 0 0 as its input and it becomes 0. But in case of OR gate, see, this OR gate receives 1 value here and this 0 value here, then it will produce 1, because the OR property says that any one of the input terminal holds 1, then the result is 1. Okay, so we'll get sum is 1. The same time we got the carry is 0, so this 0 can be evaluated from this circuit diagram. Okay, so this is half adder. In case of half adder, we can have only 2 bits can be possible, can perform the addition process. What will happen when carry is there? Okay, for example, say if we have a 2-bit number. Okay, for example, number is 0, okay, 1 0, sorry, 0 1, and we have to add 0 1. Okay, so see, just look at this column. This column having two input values 1 and 1, it produces sum 0 and carry 1, and the carry is moved to the next column sequence or next column of addition, that this one. So when we look at this column, then what are the values? How many values are here? This is the one value, this is the second value, this is the third value. So that means for doing this addition of this column, we have 3 values or 3 input values, which is not possible in case of half adder. So this is one of the drawback in half adder. So this drawback can be removed in full adder. Okay, because in full adder, uh, this adder circuit use 3 bit to do the addition process. Okay, okay, as I said, full adder is a combinational circuit which add 3 bits of binary number. Okay, so this is our block diagram of full adder. In block diagram, having 3 input terminals and 2 output terminals. This input terminal is A, this is B, and the third one is the carry of the first one, or here it is represented as carry in, I mean carry initialization. Okay, I have written here carry in. Okay, so carry in. So this full adder takes 3 input values. Okay, in form of A, B, and C, and it produces the same. One is sum, another is carry. So then now this carry will move to the next addition column. Okay, So this is basically represent as C or C out. We can represent as C or we can represent as C out. So suppose here A value can be 0, V value can be 1, and C value can be 1. Okay, so this full adder takes 1 plus 1, sorry, it should be 0 plus 1. Okay, 0 plus 1 plus 1. Okay, after that, this system when receive these values, it will just add these three numbers and it produce one is carry sum, another is carry. Okay, so as this system has three input terminals, so as per the rule of 2 to the n, it have 8 number of input sequence. Okay, 8 number of input sequence can be supplied to the system, so that we'll get S as a sum and C out is a K. So this is the functional table, okay, of this full adder, and we just got the idea of about the functional table from this block diagram of full adder. Okay, this is three input values A, B, and C in, and it has two output values. One is sum, another is carry. Okay, so as the system receives 8 combinations, so it starts from 0, 1, 2, 3, 4, 5, 6, and 7 combinations. So when we add 0 plus 0 plus 0, we'll get the sum is 0 and carry is 0. So similar way, when we add 0, 0, 1, then we'll get 1 is sum 0. So similarly, we'll get here sum is 1, 0, and 0, 1, 1, 0, 1, 1. So according to that, we will get the sum value and carry value. In the last case, when we add 1 plus 1 plus 1, we will get the summation 1 as well as carry is also 1. Okay, then our next job is to just look at this column, sum column, and we have to find out the how many ones are there, or at what time this sum terminal is an active state. Okay, or it receives the one value, and from that we have to check that what is the value of the input side, or in very simple, when s equals to 1, what are the input values. Okay, so this is first one, this is the second one, this is the fourth one, and this is the sorry, this one the fourth one. Okay, we have 4 active state, so we have to find out the equation. So s equals to, so this for this first case. Okay, for this first case, this a is 0 and b is 0. So as we know that 0 0 means that is a not operation, or it's the complement form. A complement, B complement, and C is 1, or C in is 1. So instead of writing C in, just I'm writing C I. Yes, it's quite difficult to write. Okay, C I, then plus. Okay, it's over. This one is over, and for this one, A is in 0. That means A is a in not operation. A is not. Then B is 1. So simply B. And this one is 0. C in is also not operation. That is CI. Again, I am repeating, instead of writing C in, here I am writing CI. Okay. These two are over. Then the next one is this one. So for that, okay. So here A is 1. That is A 1. B 0, C in 0. That means B naught and C in naught. Okay, this is also over. and the last case, this one, all are 1. So just write A, B, C, A, B, and C. So this is our equation for S. Okay, this is our equation for S. Similar way we can find out the equation of C also. Okay, okay. One important thing is that we can simplify. When we simplify this equation, we'll get that equation as, okay, no, we, okay, leave it. Okay, leave it, this one. So let's see about this C. C equals to this one. For this one, A is not, B, C, A not, B, C, okay, plus for this one, A, B not, C, A, B not, C, plus this one, A, B, C in, A, B, C. For this one, plus all are 1. So A, B, C, A, B, and C. So we can simplify this equation. Okay, uh, it is not simplified, it can be simplified. Okay, so after simplification, it is AC in plus AB plus BC. So this simplification is possible just by using the Boolean algebra. By implementing Boolean algebra, we simplify this equation to this one. Again, further we can simplify just by taking the common of C of I. So it becomes AB plus C of I, or C of n, within bracket A plus B. Okay, we can simplify it, or we can write, but that is not required. Okay, so we got this C, that is carry equation, and we got that sum equation. Okay, so in carry, I will do the circuit diagram for this carry equation. You have to do this one. Okay, try this one, otherwise I will discuss in the next class. Okay, for the C, for this carry, we have 3 combinations, 1, 2, 3. Okay, 3 AND operation. Okay, there is no use of the NOT gate. So here that is A, C, I, yes, then AB, here from here I can write A, this is B, and BC. C value, Cn value. Okay, so this is the result of C carry. Okay, so okay, let's see. Just giving the input value at A, B, and C in, whether we are getting correct C value or not. Just look at this one, or we give this input value. Okay, A is 0, so this is 0 value. B is 1 and C is 1. Here this is B is 1 and C is 1. So this produces 0. Okay, so this is 0 value here. A 0, B this is 0, and for this case, that is B is 1. Okay, then this C is 1. This value is 1, and this 0 0 1 supplied to this OR gate will get 1. Okay, will get the same result. Similarly, you can just use the other input values and check that whether we are getting the correct carry value or not, and you try to draw the circuit diagram for this sum value or sum equation, and otherwise I will discuss this in next class. You try by yourself. Okay, so thank you so much for today's class. In the next class we will discuss uh, that circuit diagram of full adder in detail, and after that we will discuss about the serial adder and parallel adder, and what are the benefits of serial adder and what are the benefits of parallel adder. We'll discuss in the next class. So thank you so much.